Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, we are going to finish our surface area lectures, or practice problems I should say, finishing off with spheres. We've done prisms and cylinders, we've done pyramids and cones, and now it's spheres time. And after this, we're going to do some things regarding like density of such sorts, and I think after that I'm kind of capping off this unit regarding volume, surface area, and that other thing involving density, if you will. But no other videos this week unless they are review videos, but no new material after this. Okay, so I'll be doing 10 practice problems here, and if you'd like to enjoy some baseball behind, I think I have the Braves beating the Giants, and they are my two favorite teams. You can understand that because I'm a local Bay Area kid. San Francisco Giants have to be atop that list there, and of course they're doing well this year. And the Braves, if that uniform didn't really help you recognize that I am also a big Braves fan. Who do I want to win? Yes. I probably want the Giants to win, but that's okay if the Braves win too. All right, guys, I'm going to go ahead and get started. I got 10 practice problems to do with you. It is involving surface area of spheres. Now, for us to do a surface area of a sphere, let's just make a little bit of sense of the formula, if you will. And my best way, actually speaking of baseball, my best way is picture that you do have a baseball here. And I'm not going to get too detailed with the drawing here, but you know how it has seams like that? Well, you know, the seams are stitched on, and they're stitched on from two different objects. And I really should have, for this video, I should have gotten a baseball with you for you. If you imagine that the stitching is kind of taken off the baseball, and you'll have one object here and another object wrapping around the backside there. And what they look like in the end is kind of two, I don't want to call them peanuts, but peanut-shaped, two peanut-shaped objects, one that looks like that, and another, let me just put another one there, another that looks like that as well. And, you know, those are the things that wrap around the ball, and they cover the entire surface. Therefore, if this could be an unfolding, if you will, this isn't the only way to do it, but if this were an unfolding, if you will, this would then be considered the surface area and a net drawing of such surface area. Now, spheres have radii. That radius is drawn from the center of the sphere in and of itself. So what I'm going to show you here is probably completely unrelated in the sense, but for you to remember the formula best. Again, this is unrelated in its way, but for you to remember the formula best, these kind of look like four circles here. 1, 2, 3, 4. And if you imagine that each of these circles had a little radius of r, even though it's not a real circle there, the area of each circle here would be pi r squared. So all four circles' area is 4 pi r squared. So the surface area of a sphere is 4 pi r squared. And again, that's not a reason behind it, like that's not like a derivation of the formula or anything, if you will, but that's kind of the best way of keeping in mind what this is if you do have to remember it, if you will. Think of it as those kind of close to four circles being made from that unfolding there, and I think that's your best way of kind of keeping in mind. Anyway, that's the formula we're going to use, which, just like the volume formula for a sphere, all we need is the radius. That's all we're trying to get. Whether it's given to us, whether we have to determine it based off information, and if that's what they're asking for surface area, there's that. All right, so let's start with problems 2 through 5 right here, where we are going to find the surface area of each sphere, leave the answer in terms of pi. It's not necessarily going from easiest to hardest because I see radius given here and I see diameter. So if we have a diameter in number 2 of 16 yards, the radius should be half of that diameter, which is 8 yards. So the surface area of this sphere here is going to be 4 pi times 8 quantity squared. And 8 squared is 64. 64 times 4 is 256. So I have 256 pi, and this is square yards here. Remember, this is area, so we are doing square units for these. And that's it. These are, I think they're easier than the other ones with formula and all that, especially because there's no fraction like the volume formula, the 4/3. But leave it in terms of pi. I know that can be a little weird. This problem may be a little harder only because I don't know what 21 squared. Oh, I do know 21 squared actually. So your radius is 21, and therefore the surface area is 4 pi times the radius squared. Ooh, but I don't know 4 times that number. So that's going to be 4 pi times 400. I think it's 441. 441. So 4 times 441 is 1764. I think 1764. pi square inches. Yeah, 21 inches in square inches. I gotta be sure. Sometimes I'm just like, I'm off my rocker with some multiplication, so I want to be sure. Yeah, 1764. All right, so that's in terms of pi there. So yeah, I'll be moseying along here. This one should be a relatively quick video. Oh, well, behind this, guys, there are composite solids, so be comfortable with these 4 sphere things here. There are only so many ways that they can present sphere problems. This time they give you the area of what we call the great circle, the one that's kind of like an equator to your Earth. It's the longest rim around, all that kind of stuff. So it's the circle that has an equivalent radius to the radius of the sphere. So if I'm trying to find this radius r, the radius is both of the sphere and of the circle at the same time. So if the radius is 81 pi, and you can, excuse me, if the area is 81 pi, and if the area of a circle in general is pi r squared, we got to set pi r squared equal to 81 pi so we can find r, the area, and let's get it in terms of pi. So divide both sides by pi, they go bye-bye, and you get r squared equals 81. If you take the square root of both sides, you get r is plus or minus 9, but because distance is only positive, we're referring to just that. So 9 inches. 9-inch radius. 9-inch nails. Anyway, so now let's find the surface area, which is 4 pi r squared. I kind of just thought of a different way we kind of get the answer. Whoops, I don't have to write that. So 4 pi r squared. Excuse me. 81, so 324. Okay. Now that's the long way to actually get the answer. You know, if it is indeed the same r here, and you already have, basically you have a quarter of it right here. So you could have just multiplied this by 4. And that's probably less obvious to you now when we get into, I think there's a hemisphere problem with you know, a closed hemisphere. So we'll do one of those when we talk about that at the same time. But yeah, we could have just multiplied by 4 off the bat. Doesn't hurt to use this though in instances when that's not the problem. Maybe it has something to do with the cylinder or volume, and then I guess you probably really do want to, you know, find that radius either way. All right, number 5 here. Once again, area. So the same thing. You could just multiply this thing by 4. Because this is the area of the great circle, it's pi r squared. If our surface area is 4 pi r squared, and if the r is the same thing, we could just multiply it by 4. How about we just go and do that this time? So surface area, 4 pi r squared, right? There's a pi r squared. So that's going to be 196 pi square centimeters. I really wanted them to do one where they gave us the circumference, but you know what? I didn't create these problems, so there it is. But yeah, otherwise solve for r by dividing both sides by pi, taking the square root, you get 7 as the radius. You should get r equals 7. In case you're dealing with it that way. All right, I'm going to keep moving forward. Let's go. Composite figures. So now we have, you know, like a pill. This is very much like we did a volume problem like this before, but now it's surface area. You have hemispheres. However, those two hemispheres together would close up to make a sphere. And keep in mind, when it comes to the idea of what we're doing in our drawings here, guys, we are playing to this in such a way that we're just doing the surface area. And what I mean by that is just the outside. So these little circles on the inside, these areas there, those aren't relevant because that's not a part of the outside of this drawing here, right? When these close up together, that's not really great. When these close up together, guys, it makes a whole sphere. And those parts are still not a part of the outside. So really what I'm going to do is find the surface area of a sphere, find the lateral area of the cylinder because the bases of the cylinder are not being considered. And I'm just going to add all that together. Anyway, those drawings don't really help when I do that kind of thing, but here we go. So I'm just going to take the surface area of an entire sphere here. Surface area of, I'll call this whole thing figure 1. Surface area of figure 1 is going to be 4 pi times the radius of 2 squared. 2 squared is 4. 4 times 4 is 16. By the way, they are telling us to leave the final answer in terms of pi. So I'm going to get 16 pi square feet just from the surface area of the sphere, which I mean I connect the two hemispheres together. Now, the cylinder, I'm just getting the lateral area only. The bases aren't considered. The lateral area of the sphere is perimeter of base times height. The base, in this case, is this circle right here, so it's circumference. So 2 pi r, 2 pi times radius is still 2, is the perimeter of base or circumference of that base there. And then times the height is 5 feet. That's the distance between my two bases. So 2 pi r times height. That is the lateral area of a cylinder, 2 pi r h. So let's just get that in. That is going to be 2 times 5 is 10, times 2 is 20, 20 pi square feet. There we go. So the surface area of the total thing is going to be adding those two together. The two hemispheres put together, just the non-circular base parts. So 16 pi plus that lateral area of that part, 20 pi. And because they both have pi, well, you can combine them. We get 36 pi square feet. And that is your surface area of your composite figure. I wouldn't be surprised if these were the same objects that we did use in the volume one. I don't know. It reminds me, like I said, pill. I think I remember talking about something like this before. Oh, we're doing surface area this time. Okay, so as far as surface area goes, and you'd have to hear more from me probably if you have more questions on it regarding composite figures. But we do have a kind of a full cylinder going on, and then kind of this part cut out, right? This is hollowed out. So when we did volume, we would take volume of the cylinder, subtract volume of that hemisphere. Here, we're going to take volume, surface area of the cylinder. There's a hole here. So this is an opening right here. And then what's inside here, this bowl, if you will, this is kind of like a wall. We do need to get that lateral area of that hemisphere, if you will. So we got to kind of play to some parts there. We're going to take the surface area of the entire cylinder. We're going to subtract the area of the circle, and we're going to add this inner wall, this bowl part, because that's now a part of our new surface. This hole is not, the bowl is. So that's as much as I can kind of explain for now. Let's start with, let's call it figure 1 and figure 2. So let's start with figure 1, the entire surface area of a cylinder there, guys. It's the lateral area, 2 pi r h, plus the area of the top and bottom base is 2 pi r squared. So lateral area plus area of both bases here. So the radius is 8. The radius of object 1 is 8 inches. The height of object 1 is 3 inches. So the surface area of object 1 of the cylinder is 2 pi times the radius times the height plus 2 pi times the radius is 8, radius squared. That's going to be, still in terms of pi, right? Yep. 8 times 3 is 24, times 2 is 48 pi, plus 64 times 2 is 128 pi, which is, I'm running out of room on this one, 176 pi square inches. So that is the surface area of the cylinder. I'm going to give myself a lot of room here because I want to keep writing over in this area. The bowl, I'm just calling it a bowl here, it's the hemisphere. Now, we haven't done surface area of hemisphere yet, but if a surface area of a sphere is 4 pi r squared, then a surface area of a hemisphere is half of that, 2 pi r squared, sort of. That's not counting the circular base part. So if you added another pi r squared on top of it, then it would be different if it's a closed thing there. But it's open because that circle is being cut out on the top. So we're just looking at that bottom part of the bowl, just you can kind of call it a lateral area if you call that other part of base. I just want that lateral area. So that is 2 pi r squared right there. So that's going to be also added into our surface area, but we are going to remove that bowl, if you will. And I will call that thing a base and the other thing lateral area, just so my work makes sense. It's organized when I write it. So the area of the base here of the second guy, area of the base of the second guy there is just pi r squared. With the radius being 2, the radius being 2 inches, we'll do pi times 2 squared, which is 4 pi square inches. Now the lateral area there is going to be 2 pi r squared. So that's going to be 8 pi square inches right there. So square inches. Now, one more time, the lateral area will be added because this bowl is a part of it, but the hole at the top, that circle, will be subtracted. It's taken away from the cylinder's surface area. So the surface area of the total thing here is going to be the 176 pi, the surface area of the cylinder, taking away the area of the circle top and adding in the area of the bowl, surface area of the bowl right there. And that's 4 pi total. So 180 pi square inches in total. That should be it. Yeah, a little work to do on composite figures sometimes. You just got to understand which parts of walls are being considered and which parts gets a little, in the way. And I think, the same thing's going to kind of happen here, even more so. Yeah, these look like the shapes that we used before. And if not, I don't know. But they probably are. They probably just use the same thing, but now we're doing volume, surface area instead of volume. All right, so we have two figures here. I got figure 1 and figure 2. I'm going to start with figure 2. I think it's just easier to work with that surface area. Remember how to do surface area of prisms. Again, so the surface area of figure 2, it's going to be lateral area plus the area of both of your bases, like that, top and bottom. So the lateral area of this thing is going to be perimeter of base times height. The perimeter of your base, 10 plus 7 plus 10 plus 7. It's a rectangular prism. And the height of this thing is 4 centimeters. So that's going to be 20 plus 14 is 34. So 34 times 4, which is 136, not pi, but just square centimeters, 136 square centimeters. I want to make sure that's right. 56 plus 80. Yeah, 136. All right, the area of the base here is just 10 times 7. That's length times width. And we get 70 there. So 2 bases. Oh, I tried to say 2 bases here. I just didn't write it. I wrote the 2 there. My bad. Lateral area plus area of both bases. So the total surface area of that thing is going to be lateral area 136 plus the area of both bases. So 136 plus 140 is 276. There we go. That's the surface area of the rectangular prism down below. Now, up top, there's another hemisphere. So that's just 2 pi r squared on top. I won't count the circular bottom even once for the hemisphere, but it is covering, that circular bottom is covering the part of the top base of the rectangular prism. So I do have to subtract the circular area once. Meanwhile, I am going to add the hemisphere surface area. So in figure 1 here, if you consider that a base and the top the lateral area like I did last time, the area of the base is pi r squared, r being 3 centimeters, pi times 3 squared, which is 9 pi. We're going to subtract this only once because I'm not going to even count it the first time in my lateral area here, or the surface area of the hemisphere, but it is covering that part of the top of the rectangular prism. So the lateral area is 2 pi r squared, which is, of course, going to be 18 pi square centimeters there. So the surface area of the total thing here, we're going to take the surface area of the rectangular prism, which is 276 pi. Not pi, just 276. We are going to add the lateral area of the hemisphere, the part that's on top, like the dome portion, and then we are going to take away the part that I am covering this with here, which is the 9 pi, taking that away, and we're going to get 276 plus 9 pi. As I combine these two to get 9 pi, 276 plus 9 pi do not combine in any sort of way. I can leave that as square centimeters like that. That would be a final exact answer if they said leave in terms of pi. I'm going to go ahead and check and see if that's what they still want. They do. They still want me to leave the answer in terms of pi. This is the answer in terms of pi. 276 square centimeters plus 9 pi square centimeters. And that's it. If you round it, I'm sure it's above 300. It's probably close to 305, something like that. There you go. All right, a few more problems here. I think 3 more problems total. Last composite solid, though. So this one's going to have the most work because to find the surface area of the cone, we are going to need the slant height here, this L, understanding that the radius of 10 would go over, say, like right there as well. Then you do have a right triangle. I know that I have to take note of that. I will call that one figure 1. I'll call the hemisphere figure 2. And it is a hollowed out portion. It's kind of like a ice cream cone, snow cone, whatever. It's hollowed out right there. So we're going to kind of, remember, we're going to take away the circle, but we are going to add in that bowl. That bowl is going to be a part of it. So let's start with the cone, though. the surface area, not volume, the surface area of the cone that we need, surface area of 1, it's of course going to be lateral area plus area of base. There's only a single base there. The area of the base, its radius is 10 millimeters. I haven't done millimeters for a while. So the area of the base here is pi r squared, which is 100 pi square millimeters. That's the area of the base there, and obviously this bowl part's going to be taken, that circle's going to be taken out, apart with the bowl. And then we need the lateral area of this thing, and the lateral area of a cone is pi times the radius of the base times the slant height. So pi r L. So we do know the radius as 10 millimeters. We need the slant height still, knowing that this is 10 and this is 24. I can tell you now it's going to be 26. But you got to use Pythagorean theorem for that. We're going to say 10 squared plus 24 squared equals L squared. So that's 100 plus 576, I think, equals L squared. L squared equals 676, and that must be 26. L equals 26 millimeters. I know because it's a 5, 12, 13 special triangle that's doubly enlarged. If you don't know what that means, that's okay. That's your Pythagorean theorem for that. So your slant height is 26 millimeters. So we are going to be doing lateral area as pi times the radius of 10, I believe it was, times 26, which is 260 pi square millimeters there. So there's the lateral area. So lateral area plus area of base will give us surface area of the cone, which is 260 pi plus 100 pi, which is a nice clean 360 pi square millimeters. All right, that was a fun one. All right, we're not done though. We do have the shape 2, the hemisphere. Remember, we are going to take out the circular base and we are going to add in the bowl inner wall, what I like to call it there. So that's going to be, let's get purple. So a radius of 8 millimeters here. Radius is 8 millimeters. And your, what I call the area of the base, that bottom portion, is going to be pi r squared. Pi times 8 squared, which is 64 pi square millimeters. And then the lateral area, what I like to call it, the part of the hemisphere, everything that's not that bowl that we're cutting out, or the circle we're cutting out, the bowl part is double that. It's 2 pi r squared. So 2, well, you double 64 pi. Double 64 pi, which is 128 pi. Looks like that's popping up a couple times now. Square millimeters. So, in total, we are going to take the surface area of the cone, the entire thing, and we are going to also subtract the hole, take out the hole there and add that in. So surface area of the total is going to be the surface area of the cone, 360 pi. We are going to take out the circle hole from that bottom, and then we're going to add in the bowl portion. Basically, these two together add up to be 64 pi. So 360 plus 64 pi is 424 pi. Total equals 424 pi square millimeters. There you go. There it is. They say leave in terms of pi, and I shall. All right, 2 more problems. I think these ones will be a lot faster. They aren't composite figures. Find the surface area of the closed hemisphere. And I kind of wish that they gave us one of these problems earlier. This is going to be relatively fast. What I do want to keep bringing about, guys, is that since the surface area of a sphere is 4 pi r squared, that ideally you might think that the surface area of a hemisphere is 2 pi r squared, because that's what we're doing. But a closed hemisphere includes that base at the bottom. And as I've kept mentioning here, you take the 2 pi r squared, this half that's the dome, like Patrick Starr's dome of a house, his rock, but then we're adding the circular bottom as well, which is another pi r squared. So in the end, guys, that's 3 pi r squared for a closed hemisphere. And it's the same radius for the entire thing. The radius that goes right here is the same radius that goes up into that part right there. Those are the same lengths. So just find the radius here, which is half of 8, because 8's the diameter. So we get 4 yards. So the surface area of the closed hemisphere here is going to be that 3 pi r squared. 3 pi times 4 squared. 4 squared is 16. 3 times 16 is 48. So we get 48 pi square yards. Now, I think these are under the same instructions as the previous thing. I haven't seen a change in instructions, so I will leave it in terms of pi. It's close to 150 square yards or so. That'll be my final answer. All right, last one, number 11. No diagram. Find the circumference of the sphere with a surface area of 60 pi square inches. Leave the answer in terms of pi. Now, when we mention circumference, we are talking about the one of the great circle, if you will. So even though they don't give me a drawing, let me give you the idea of what we're trying to find. We want to find this circumference around, again, the great circle, if you will. So the one where once we crack the radius, that's what we need. Once we crack the radius, then we have the information to get circumference, as circumference is 2 pi times the radius. Okay, so the surface area is 60 pi of the entire sphere, and a sphere, of course, is 4 pi r squared. So that is 60 pi. I can probably knock this part out here. So let's solve for r in this sense when we have this information here. Let's divide both sides by pi for sure. Those are gone. It looks like I can divide both sides by 4, and I'm going to get r squared equals, r squared equals, 15, not a perfect square. When I take the square root of both sides, I get r equals the square root of 15 inches. It's close to 4. 3 point something. I don't know exactly what, but here's the thing. We're not rounding. Even if we were, they say leave in terms of pi, even if we were, we don't round early. So this square root of 15, might show up in our answer, and you have to be okay with that. So the surface area in we want the circumference. The circumference in the end here being 2 pi r, 2 times pi times your radius, that's it. 2 pi root 15 inches. They said leave in terms of pi, which means I want to not approximate anything else. Square root of 15 is exactly that. 2 times root 15 isn't like root 30. That would be root 2 times root 15. And left in terms of pi. That would be it right there. Kind of interesting look. If you, again, want an approximation here, we'll have to multiply by 3 a couple times. It's probably close to 24, 25 inches in total. Remember, it is circumference. It's not square inches. But that would be my final answer. That's it. All right, those are all the problems I wanted to do there. Looks like the composite figures kind of ended up adding in my time a little fly out at the wall. Added up my time a little bit there, but I hope that those hemisphere things made sense and the composite figures as well. That's all I got for you. Let me know if you have any further questions. Leave in the comment section down below. And like I said, my next video you'll see will be likely a review of sorts of all surface areas. And we saw them all. We just saw some things of cylinders, prisms, and cones, and prisms, cylinders, and cones. We didn't see any pyramids. But everything else was kind of applied here, even in the composites. And then the spheres on top of it in hemispheres. So that'll do it for this, guys. This is Mr. Robinson. Thank you so much for watching. Take care.